Welcome back to analyzing voltaic cells. This is one of the more straightforward ones. I kind of wonder if this shouldn't have been our first example in the section, but that'll be okay. So, as we have learned, you can set up any voltaic cell by getting two glass beakers and putting a salt bridge between them like so. You'll have some kind of electrode in each beaker. Connect a wire onto both of them using some alligator clips. Pour some liquid, probably water, into each container. This is your basic template for a for a voltaic cell, and you can assume you've got all this stuff before you even look at the components. Now, they tell us that we have a bar of nickel, a solution with nickel ions, a bar of copper, and a solution of copper ions. And presumably we have water because it's hard to make solutions without it. So, armed with all that, we can go to our data book, the redox table, and start looking for our strongest oxidizer and strongest reducer. So, going down the left side, we're looking for basically copper, nickel, or water. So no, copper, nickel, water, copper. Here's water, but it's with hypochlorite ions, so that's nothing to do with us. Nitric acid, no. Copper. At 0.34 volts, we find copper ions. Sorry, I shouldn't just say copper. Copper ions are our strongest oxidizing agents. So this reaction is going to happen as written on one side of our cell. And the other thing that will happen, our strongest reducer, is lithium's no good. No. We're looking for copper, nickel, or water. Copper, nickel, water, copper, nickel, water, copper, nickel, water, copper, nickel. Here we are. Nickel. Nickel metal will be our strongest reducing agent. And because we're starting this reaction on the right side, we have to go right to left. It'll be nickel metal turning into ions and electrons. The water didn't do anything in this reaction. So, coming back to our cell, what we got out of the data book is that our strongest oxidizer is copper ions. They're going to take electrons from someplace and turn into copper metal. And our strongest reducer is nickel metal. It's going to convert to nickel ions and release a couple electrons as it does. So, what's this going to look like in the cell? Copper ions are going to pick up electrons and turn into copper metal. So these ions are going to go over to the electrode, pick up electrons, and stick and turn into solid copper. So we're going to have more and more copper metal forming on this electrode. It's going to, at first it'll look like it's getting furry because you get little filaments of metal forming on it. And then it'll start getting fat as more and more copper forms on it. So this copper electrode is going to grow and build up as it gains mass. This one will gain mass as more and more copper sticks to it. Another thing to notice, this reaction, is this taking in electrons or losing electrons? Electrons are flowing into the copper. So today the electrons are going that way. And if this electrode is gaining electrons like this, then Leo says, Grr, this is a reduction that's happening on the copper side. And reduction has the letter C in it, so this side must be our cathode. If electrons are flowing into you, then reduction is happening there. That makes you the cathode. So that covers the copper side. Over on the other side, nickel metal is dissolving into nickel ions. So we're going to get more and more nickel ions out in the solution here. And If we're losing solid nickel to do that, the nickel electrode is going to dissolve and erode and shrink. So we're losing mass on the nickel side. How about electrons? Are electrons being gained or lost on the nickel side? We start with nickel, and this reaction makes nickel ions, and it makes electrons. So electrons are going to start flowing out of this electrode. They're all negative. They don't like each other. They are leaving. So both sides agree electrons will flow out of the left into the right. And if this side is losing electrons, like they're flowing out, Leo means losing electrons is oxidation. Oxidation has a letter A in it, so this side must be our anode. If you're losing electrons, if electrons are flowing out, you're in oxidation and you're happening at the anode. Electrons, well, we've got nickel releasing nickel ions, so positive ions are flowing out this way and are going to start going up through the salt bridge. Over on this side, copper ions are being sucked into this electrode and turning solid, so all our positive ions are going to be moving left to right. If this cell had any negative ions, they would flow the opposite direction, right to left. Another way you can think of that is negatively charged electrons are flowing into the right side, making the right side more negative. So negative charges see that and go, ugh, more negatives coming in, I will leave. I will flow in the opposite direction to get away from those incoming electrons. Let's talk about ion colors real quick, because sometimes they'll ask about that. If you look in the ion color chart, which is, let me show you this. There we are. On page 11 of the data book, there is a list of ions that have really visible colors. Chromate ions are yellow, and what this is in really high concentrations, chromate ions are bright yellow. Really watered down, they're pale yellow. Chromium ions are blue-green, or they look just greenish when they're more dilute, and so on like that. In this cell, we're seeing nickel-2 ions, which they say are bluish-green, or pale blue-green, not surprisingly if they're diluted. And copper ions are brilliant blue, or pale blue if there aren't so many of them. So knowing that, we can see this would be a pretty colorful cell. We're going to have, over on the right, let's go green. The nickel reaction produces nickel ions, so we're going to start seeing a stain of bluish green ions forming around the nickel electrode. And that bluish green is going to start to spread out through the cell, filling more and more of the solution. As long as this reaction goes, we'll get a stronger and stronger blue-green look to the nickel side of the cell. And eventually that blue-green will even start to work its way up the salt bridge. Meanwhile, on the other side, this solution with the copper ions will start out blue because copper ions have a bright blue color, but what happens to it? The copper reaction takes copper ions and turns them into copper metal. So this blue color is going to start to fade. It'll start out bright blue, and then bright blue will disappear as those ions get sucked into the cathode and turned into copper metal. So weirdly, bright blue ions turn into shiny orange copper as the reaction goes on. So blue-green will start to spread through the entire cell, and the blue color of the copper ions will fade. Can we do two of these in one video? Let's find out. Graphite electrode and acid permanganate. Okay, let's start. Before we even get into the ingredients, let's draw the things we know are going to be there. Tube of jello, electrode, alligator clips, wire, Pour some water in there. Okay. There's a general purpose cell ready to go. And they tell us we have a graphite, that's copper, electrode in an acidified permanganate solution. And we have a lead electrode in a lead-2 sulfate solution. So lead ions, sulfate ions. And of course there's H2O in all of this. So back to our data book. I'm on the wrong page. There we are. Okay, so we are going to tear around through the redox table looking for our strongest oxidizer and strongest reducer. Good news. Very quickly we find acid permanganate. We use this one a lot because it's colorful and it's really strong, so it works well. Acid permanganate is our strongest oxidizing agent. Permanganate by itself doesn't do much. Acid by itself is much lower. It's down at 0 volts. But permanganate and acid together are a very strong oxidizing agent. And when we go looking for our strongest reducer, we're going to have this is lead with sulfate. That's not what I thought I would find. Here we are, lead. Lead metal. I'm sorry, I shouldn't have mentioned this anyway because this is lead metal. Actually, this is interesting. We're going to get lead, metal, and sulfate as our strongest oxidizer. Not just the lead. The sulfate makes it a stronger reducing agent, so this is actually what's going to happen. Lead, metal, and sulfate will turn into PbSO4. Okay, so armed with that, let's get back here and fill in our reactions. We have the acid permanganate reaction is our SOA. MnO4 minus plus, I forget the numbers for this one, 18514. Okay, so 8 hydrogen, 5 electrons, and that makes 1 manganese 2 and 4 water. Okay, that's our SOA reaction, and the SRA was the slightly unexpected lead metal plus sulfate ion. Turns into lead sulfate and 2 electrons. Okay. So in our strongest oxidizer, we have MnO4 and hydrogen are going to turn into manganese ions, so these will continue to float in the solution. We'll make water, so there won't be anything depositing onto this electrode. There's just ions forming on the surface and then floating away. This reaction consumes electrons. So we have to have electrons flowing into the acid permanganate side to keep it going. If electrons are flowing in, that means you're gaining electrons, which means you are a reduction. Reduction has the letter C in it, so this must be happening at our cathode. If electrons are flowing into here, then they must be flowing out on this side. If you're losing electrons, then what's happening over here is an oxidation. Oxidation has a letter A in it, so that must be happening at our anode. Again, slightly different way to reason it out, but same results, as long as you have one way to do this that you're comfortable with. I think you will be fine. If you're getting messed up on this, please talk to the instructor and get it straightened out, because we want you to have some way of doing this that consistently works. Over on this side, lead metal, solid, is reacting with sulfate and forming lead sulfate, which is also solid. So there's going to be a layer of lead sulfate forming on top of our lead electrode. PbSO4 will coat the electrode and plate onto it. And this reaction shows that it's going to release electrons. So again, that makes sense that electrons will flow out of this electrode. They'll accumulate in the lead, and then because they have negative charges and don't like each other, they start fleeing over to the other side. So we've got our oxidation, anode, reduction at the cathode, electron flow, and if lead ions are being consumed, actually positive ions are being consumed on both sides. That's not a good guide. If I were working out ion flow for this one, I think I would look at the electrons. If electrons are flowing into this side, then this side is getting more and more negative. Negative ions that see these electrons flowing in are going to go, ugh, negatives. I'm leaving. Negative ions will flow this way, left to right, through the salt bridge to get away from all those electrons coming in. Or, another way to think of it, these negative ions are called anions. They will flow toward the anode, like we normally see. When negative electrons flow into this side and it starts going negative, positive ions see that and go, ooh, interesting, I love negative charges. Positive ions will want to flow right to left, toward the left side. So it makes sense that positives will flow the opposite direction from negatives. It also makes sense that positive ions, which we call cations, will flow toward the cathode. So the cathode attracts cations, which means positive ions. The anode attracts anions, meaning negative ions. So things like permanganate are going to be tempted to flow towards the right side. They're going to be pulled towards it. And positive ions like the lead will want to flow right to left because they're attracted to the cathode. I think that covers all the things. Hope you're getting comfortable with this. If not, please get a hold of the staff and we will be happy to go over it with you.